This is chapter 4 of class 11 science chemistry, okay, ISC syllabus. Now, in this chapter, I'll just tell you the objectives of this chapter quickly. In this chapter, you'll be able to, after going through this chapter, you'll be able to understand the main cause of chemical combination. I will give you an idea also about the Kossel and Lewis approach to chemical bond formation and as well as the Octet Rule. Moreover, in this chapter, you'll be learning about the formation of covalent bond, ionic bond, coordinate bond, hydrogen bond, and you get some idea about the van der Waals forces existing between covalent molecules. I'll be teaching you also how to write Lewis structures of simple molecules. In this chapter, I'll be teaching you about hybridization involving the orbitals, the s orbital, the p orbital, and the d orbital. I'll also be teaching you how to predict the shapes of simple molecules by the help of a theory which is called VSEPR theory, valence shell electron pair repulsion theory, along with hybridization. In this chapter, I will also help you to understand dipole moment in polar molecules. Okay, we will be learning about some more examples of resonance in this chapter and limitations and understanding of valence bond theory. Okay. Then at the end of this chapter, I'll be teaching you very nicely in the best possible manner the latest theory under this chapter, which is called molecular orbital theory, which is the most interesting and the most important part of this chapter, where under molecular orbital theory, I'll be using this theory to apply this theory for forming homonuclear diatomic molecules and even molecular ions. Okay, so after that, you'll be able to understand the metallic bonding on the basis of models, the band theory and the electron C model. Okay, so with these words, for the main objectives of this chapter, I begin this today's chapter. Okay, so the first thing that I would like to say is the word chemical bonding. Now, in very simple language, chemical bonding, it is nothing. It is nothing. In fact, it is nothing. It is a bonding. It is an attractive force which holds various constituents, and those constituents can be atoms or they can be ions, which are held together in different chemical species. And this attractive force, it is called a chemical bond. Okay, so that is the basic approach to this chapter, chemical bonding. Okay, now moving further to the first and the most important approach to chemical bonding. There were two people, Kossel and Lewis, together who contributed to the study of this chapter systematically, and they were Kossel and Lewis. Kossel Lewis approach to chemical bonding. Now, the first point, Lewis postulated that atoms achieve a stable octet when linked via chemical bonds. If you link atoms, one atom to another atom, they link to each other by means of a chemical bond. So after forming a chemical bond, their octet is achieved, their octet is reached. That is the postulate which Lewis has given. Now, in the case of bonds formed from hydrogen or fluorine, etc., the bond formed from sharing of electrons between the atoms. Here in hydrogen, fluorine, these are all covalent compounds. So the bond existing in these molecules is basically a covalent bond. In this case, each atom attains a stellar outer electronic configuration by acquiring 8 electrons after the bond sharing, electron sharing. Then also, moreover, Lewis symbols. In the formation of molecules, only outer electrons or group balance of the electrons take part in chemical bonding, and hence are called valence electrons. So valence electrons are nothing but the electrons present in the outermost shell which participate in bond formation either by sharing or by complete transfer. In electrons of the orbitals of sp and d and f orbitals do not take part in chemical bonding. Only d orbitals take part. So this is what Kossel or Lewis had to give us. So remember this: sp and f orbitals do not take part in chemical bonding according to Kossel and Lewis. Only d orbitals take part. Okay, so this is one important approach. After that, looking to some more points over here, the very first important postulate which was pictured by Lewis was in an atom in terms of positively charged kernel. In the center, there is a kernel, the nucleus plus the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. So if there is a nucleus in the center, it contains electrons which are completely filling the subshells, and outside it there is a shell or a subshell containing which can accommodate a maximum of 8 electrons. So that was according to Lewis. Lewis also postulated that atoms achieve the stable octet when they are linked by chemical bonds. So as soon as atoms combine, they form a chemical bond with other atoms. By sharing electrons, they achieve an octet. Moving further to the theory part, the octet rule. Atoms, generally, the atoms bond because it results in a more stable electronic configuration. That's why atoms bond with other atoms. Atoms bond together by either transferring or sharing electrons. So there is transfer, there is sharing of electrons, so that all atoms obtain an outer shell with 8 electrons ultimately. That's why we have an octet rule. Okay, octet rule means what? The ability, the capacity of an atom after sharing to acquire 8 electrons. But there are some exceptions to this rule. The key to remember is to try get an electron configuration like that of a noble gas. So how to become more stable? If you want to become more stable, if you are an atom, then you can become more stable by acquiring a configuration something like that of a noble gas. After that, moving further to the octet rule, it is a tendency for atom to seek 8 electrons in their outermost shells. Natural electron configuration of the noble gas contains 8 electrons. It is done by gaining or losing or sharing electrons. This increases stability. And remember, hydrogen and helium seek a duet. Hydrogen and helium, they seek a duet. Okay, that is important. So only hydrogen and helium, they seek a duet means they they want to acquire 2 electrons in their valence shell. Okay, so that is octet rule. After that, coming to one important concept. Look at on your screen. Can you see a screen? Can you see a screen?
Yes, sir.
There is a structural formula of a compound. There is a structural formula of a compound CS3 NH, then it is CHF, then there is OH. Structural formula of a compound. It's a compound of carbon, hydrogen, nitrogen. Okay, and there is OH also over there. Okay, now just look at the structural formula carefully and focus your eyes to this carbon. On this carbon, if you see, there is no lone pair. So electrons in lone pair is 0. On this carbon, there are no lone pairs. So 0 lone pairs. Then electron in bonds. 2 electrons here. 2 plus 2, 4, 5, 6, 7, 8. So electron in bonds is 8. There are 8 electrons around carbon in the form of bonding electrons. So total valence electrons becomes 8. Okay, for this carbon. Then focus your eyes to this nitrogen now. This nitrogen has a lone pair over here on it. So electrons in lone pair is 2. And electron in bonds is 2 over here. 2 over here and 2 over here, that is coming to 6. So total valence electrons, it is 8 for this nitrogen. Then focus your eyes to this fluorine over here, fluorine atom, which is linked to this carbon. This fluorine atom, electron in lone pair is 2 plus 2 plus 2. That is 6 electron in lone pairs, and one bond is there containing 2 electrons. So there is electron in bond is 2 electron. Total is 8. Okay, I am trying to explain you octet rule. If you see, here also after bond formation 8 electrons. Here also 8 electrons. Here also it is 8 electrons. Okay. If you focus your eyes to this oxygen over here, you will see electron in lone pairs is 4. 2 over here, 2 over here, and in bonding pairs 1 to 1 to 4. So it is coming total 8. Okay, so if you look at all the electrons except this hydrogen over here, all are acquiring 8 electrons. So that is the octet rule practically. Okay, but if you look at this hydrogen, hydrogen has no lone pair. Electron in bond is 2, 1 and 1, 2. So total number of valence electron is 2. So hydrogen tries to acquire a duplet. Hydrogen tries to acquire a duplet in order to become stable. So this is one practical application of the octet rule. So atoms combine with each other to acquire an octet after the combination. So that was explanation for the octet rule. Now coming to exceptions for the octet rule in the next slide. Now there are exceptions to the octet rule as well. There are two elements which don't want an octet of electrons, and those elements learn them: beryllium and boron. Beryllium wants 4, boron wants 6 in the examples over here. Have a look. Okay, beryllium wants 4 and boron wants 6. Have a look. This is boron, BF3. Okay, this one is I think BH3. Okay, now here if you look at that, after bond formation, after combining with fluorine atoms 1 2 3 4 5 6, here also BF, this is BH3. Okay, it is having 6. If you talk about beryllium, Be, you can have Cl4, BeCl4. Okay, in BeCl4 it is having 4 electrons around it which have combined with 4 fluorine atoms. So these are the two elements which you must remember, those who don't want an octet of electrons after combining with other atoms. Okay, that is the first exception. Moreover, if you move to the third row and heavier elements, they often satisfy the octet rule but can exceed the octet rule using their empty valence d orbitals, especially when surrounded by highly electronegative atoms such as chlorine or bromine and oxygen. Okay, now look at sulfur. Sulfur, it is an expanded octet. After combining with fluorine, it is forming sulfur hexafluoride, SF6. So 2 electrons here, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 electrons after bond formation. So it is an expanded case of expanded octet, more than 8 electrons after bond formation, because this fluorine atom, it is an electronegative atom. Another example is PCl5. If you look at phosphorus pentachloride, then around phosphorus there are 2, 4, 5, 6, 7, 8, 9, 10. There are 10 electrons which are participating in bond formation. Okay, so here also in the case of phosphorus pentachloride, we see a case of expanded octet, which is an exception to the octet rule. Now, moving to the next slide over here, incomplete octet. When I was talking about boron trifluoride, okay, incomplete octet. Incomplete octets occur when central atom has less than 8 electrons in its valence shell. The beryllium, boron and aluminum cannot achieve octet configuration even after sharing electrons with other atoms. Like for example, boron, it has 5 electrons in, so 1, 2, 3, 4, 5 in the valence shell. So it has 1, 2, 3 electrons over there. It can be used to form bonds. After sharing also, total number of electrons, it is not an octet. It is only 6 electrons over there. Okay, it is only 6 electrons. But fluorines, the 3 fluorines have acquired an octet. Okay, so this is a case of incomplete octet. Okay, now another example over here, you can have a look. The case of expanded octet. Some species in the third period and beyond exceed the octet rule. Empty 3D subshell or higher can accommodate extra electrons. Terminal atoms, usually halogen or oxygen, are used. Never occurs within second period elements. Okay, so example is xenon XeF4. XeF4 1 2 3 4 5 6 7 8. See, after sharing, it is what? It is having more electrons. It will be having more electrons, 1 2 3 4 5 6 7 9 10 10 electrons, because there are still two more lone pairs left from the xenon. Okay, now look at this phosphorus pentachloride. Again 1 2 3 4 5 6 7 9 10 10 electrons there also after bond formation. Okay, so here it is there, I3, talking about I3. Okay, I3, so here again it is exceeding an octet over here. So these are examples of expanded octet which are not obeying the octet rule. Now have a look at this screen on your cell phones, on your laptops. Have a look carefully, then I will ask you a question. Go through them very, very carefully. Okay, did you understand something? Dear boys, did you understand something?
Yes, sir.
Okay, these structures which you see on your screen, no? This is the Lewis structure for carbon tetrachloride, CCl4. Carbon in the center, surrounded by 4 chlorine atoms, and the carbon has acquired an octet, 2 4 5 6 7 8. This is the Lewis structure for ammonia gas. Ammonia gas. In ammonia gas, the nitrogen has a lone pair surrounded by 3 bonding pairs. This is for ozone. You must have heard of ozone, O3. Lewis structure for ozone. This is for phosphorus trichloride. This is for chloroform. This is the Lewis structure for nitrogen. This is the Lewis structure for nitrite, NO2 minus 1. Okay. Resonance structures, resonating. Okay. This is NO2, nitrogen dioxide, beryllium chloride, BeCl2, 1, 2, 3, 4. Okay. What do you call this? Is not acquiring an octet, exception to the octet rule, beryllium chloride, dichloride. This one is carbonate, CO3 minus 2. This one is methane, Lewis structure for methane, and this is the Lewis structure for sulfur dioxide gas. Okay, so these are examples of Lewis structures which I am giving you, and I expect you all to be able to draw them. This is an important one. Okay, this is also an important one. This is also an important one. This is also an important one. Okay, even carbonate is important. Okay, others are easy for you. Okay, so according to the Lewis structures, so you should be able to, in the examination, if it is asked, draw the Lewis structure for so and so, you should be able to draw. Okay, now, like for example, if they ask, draw the correct Lewis dot structure for sodium chloride. So this is how you draw. You have to write down Na. It has one electron in its valence shell, so put one electron. And Cl, chlorine atom, it has 7 electrons in its valence shell, so put 7, and then with the help of arrow show this, and then after that draw the structure. Na will acquire a positive charge, and then Cl 1, 2, 3, 4, 5, 6, 7, 8, and then minus charge on the chlorine atom. So this becomes the Lewis structure for sodium chloride. Okay, so that is how we are going to draw the Lewis structures. Okay, now moving to the next slide. Important ones. Lewis structures, Lewis representation of ionic structures. One is magnesium oxide. These are in the syllabus, and this is how the questions are asked, and this is how you should do in the examination. Magnesium atom, oxide ion, oxygen atom. Okay, so both the electrons are transferred, so you get Lewis structures for magnesium oxide. Lithium oxide, similarly. Okay, lithium oxide. Okay, then next slide, you look at the next slide. Lewis electron dot symbols for calcium oxide, which is in the syllabus. Calcium oxide, Ca, both the electrons are transferred to the oxygen to form calcium ion and oxide. So this is how you will show the formation of calcium oxide by Lewis electron dot diagram. Then magnesium chloride. From the magnesium, both the electrons are transferred, okay, to the fluorine atoms, and you get MgF2. Okay. Then sodium sulfide over here. Sodium, two sodium atoms. They are transferring one electron to one sulfur, another electron to the same sulfur. Both the electrons to the same sulfur, and that's why you're getting Na2S. So this is the Lewis structure for sodium sulfide. Okay, so are you getting the idea clear, my dear boys? Are you getting it? Are you getting the idea very clear? The Lewis structures. Okay, now let us look at ionic bond. Ionic bond. Now, an ionic bond, the complete transfer of electron from one atom, normally metal, to another atom, non-metal, is called ionic bond according to class 10. This is what we have learned in class 10. But if you write the same definition in class 11, you are not wrong. You are not right also. You have to have a better understanding because you are in class 11 and 12 ISC chemistry. So you'll have to provide a better definition for that. And you have learned the formation of ionic bond between sodium and chlorine atoms to form sodium chloride molecule. Okay, now this sodium, it has one extra electron, and this chlorine it needs one electron to complete the octet. So they transfer. So metallic atom transferring the electron to the non-metallic atom to complete its octet. After losing one electron, its octet is complete in the inner subshell. Okay, so that is how we understand ionic bond. But today, if you look at the definition of an ionic bond, the bond which is formed by the electrostatic attraction between the cation. This is the correct definition according to the ISC level, plus 2 level. The bond formed by the electrostatic force of attraction between the cation and anion, which are produced by complete transference of electrons from one atom to another, it is called an ionic bond. Example is, plenty of examples are there: sodium chloride, magnesium oxide, aluminum oxide, etc. Now, let us go quickly, immediately to the conditions required for the formation of ionic bond between two elements. This you must remember. This is important. The conditions required for the formation of ionic bond in detail. Okay. Okay, you must know this. The first condition is the two elements must be of opposite charge. Means one must be a metallic ion, another one must be a non-metallic ion. Then the next point is an element must have low ionization enthalpy, the cation. That means it should be possible for the cation to easily lose electrons, or the metallic ion to easily lose electrons and become a cation. The next point is another element must have higher value of electron gain enthalpy, that is the anion. Then the difference of electronegativity between the elements must be greater than or equal to 1.7. So please try to remember this value. It will not harm you. It will do you good if you remember this value of the electronegativity difference. Then next point is high lattice energy of the compound formed. Now I'll talk about lattice energy. Lattice energy is the amount of energy required to form 1 mole of a solid substance from its ions. If 1 mole of a solid substance is formed from its ions, the amount of energy required to do so, that energy is called the lattice energy. So for the formation of an ionic bond, we need a high lattice energy. So these are the basic important conditions for the formation of ionic bond. So let us have a look at them in detail. Okay, now with regard to ionization energy over here, if you look at the ionization energy on your screen, metals, they generally have 1 to 3 valence electrons with lower ionization energies, so that is good. Non-metals have 5 to 7 valence electrons, higher ionization energy as well. Noble gases have complete octets. Helium has 2 valence electrons, highest ionization energy in a period. So for the formation of an ionic bond, required conditions, metal should be there, non-metal should be there. Now talking about the important point over here with regard to lattice enthalpy, lattice energy. For an ionic compound, the lattice enthalpy is the heat energy released when 1 mole of a solid substance in its standard state, solid state, is formed from its ions in the gaseous state. So the ions which are in the gaseous state, when they combine to form 1 mole of that substance, whatever is going to be formed, and which results in the amount of heat energy which is given out. Heat energy is given out. That heat energy which is given out when the ions when the ions combine to form 1 mole 1 mole of the solid substance in its standard state. So that heat energy which is given out, it is called lattice enthalpy or lattice energy. Example is given over here. But lattice energy cannot be determined directly. There are indirect methods only. Experimental data is used for the IP, for the EA, for the sublimation, and so on. So to solve problem based on this enthalpy cycle, the Hess's law is used to get the standard heat of formation of a solid substance, ionic compound. Okay. Now, enthalpy cycle is based on the formation of compound from its elements in their standard state. So, I think the concept of lattice enthalpy is clear to all of you. I'll explain once more. For an ionic compound, the lattice energy is the heat which is liberated. The heat which is liberated when 1 mole of this solid in its standard form is formed from where? From its ions in its gaseous state. So that energy which is given out to form 1 mole of the solid substance in its standard state, that energy is called lattice enthalpy or lattice energy. Okay, now come to the factors affecting lattice enthalpies. Basically, lattice enthalpy depends on two factors. The first one is ion size. Remember this. This is an important chart. This is an important chart. The ion size. Small ions are required, are close to each other and exhibit stronger attraction. When charges are same, smaller ions have higher lattice energy. So, for ionic compound to form favorably, we must provide small ions. I'm talking about the cations, smaller cations. Okay. Then the ionic charge. Ions with higher charges exhibit stronger attraction. When size is smaller, higher charges lead to higher ionization energy. So the two conditions are ion size should be small. The size of the ion should be small and the charge of the ion should be large. Then only it will favor higher lattice enthalpy, which is going to favor easily the formation of ionic compounds. So in short over here, what are the factors affecting lattice enthalpy? The factors affecting lattice enthalpy towards formation of ionic compound is small ions, small ions having larger charges. Small ions having larger charges, they favor high lattice enthalpy, resulting in the formation of ionic compounds favorably. Okay, so that was regard to lattice enthalpy. Now it is almost time. Okay, anyway, I will stop over here. Okay, so I'll continue with the next topic in my next class, that is tomorrow. Tomorrow I've got a double period with you all, that is tomorrow is Thursday. The first period and the first, second, third, fourth, sixth period, 12 o'clock till 12:40. Okay, so I'll stop my class here only. Before that, I will record the attendance. Then only you may leave the class. Okay, and go for lunch. Okay, boys, just hang on over there for quite some time. Let me record the attendance. Then only you leave. So, but please don't forget to revise whatever has been taught to you all. Okay. Okay. Can you see your screen now?
No, sir.
Now, can you see your screen? Your screen, not my screen.
Yes, sir,
Yes,
we can see
sir.
your screen.
Yes, sir.
So your attendance is downloaded. Okay. So thank you so much. Have a nice day. Let's meet tomorrow.